Okay, this is part two of reciprocal functions. Here's where we're going to describe the difference between reciprocal and rational function. A rational function is when you have two polynomial functions and you're dividing them. So when you add, subtract, or multiply polynomial functions, the result is always a polynomial. Because when you add or subtract, you're just adding or subtracting like terms. So your x cubes would go with your x cubes, and then you'd simplify them, and you might end up with more or less or no x cubed terms. And you can do that with all the different powered terms. When you multiply, you're just increasing the degree of your polynomials, but it's still a polynomial function. Like if you multiply a degree 2 polynomial by a degree 2 polynomial, you end up with a degree 4 polynomial, but still a polynomial function. But when you divide polynomials, the result is a rational function. So a rational function is just dividing two polynomial functions. Where it's different from a reciprocal function is a reciprocal function is just 1 over an original polynomial. So let's say our original polynomial was 2x minus 1. If we wanted to find its reciprocal, we would just do 1 over 2x minus 1, and that's a reciprocal function. Where they're similar is that reciprocal functions are rational functions because f of x equals 1 is considered a polynomial function. Its degree is 0. It doesn't have an x term with an exponent. It kind of does, but it's hidden. It'd be x to the exponent 0. And the denominator, 2x minus 1, is also a polynomial function. This is of degree 1. So we have a degree 0 divided by a degree 1, so technically we have a rational function. So to graph a rational function, we can do a full analysis of its properties, and we can use those properties to graph it. And that's what I'm going to show you here. This is a very long way to graph this function, but it's going to illustrate the process we're going to go through for graphing every single rational function we do this unit. Even the difficult one we're going to do as a part of our sketching assignment later in the unit will follow this process. A much easier way to graph this particular reciprocal function would just be to graph the line and then apply the properties of reciprocal functions like we just did in video 1. That'd be a very easy way to get the sketch. But since I want to show you the process for graphing all rationals, we're going to go through that process. And that process follows answering these questions, these prompting questions. So here we go. First, we're going to consider our function, and we're going to state any restrictions on that function. So a restriction is that any number that x can't be. And where you find restrictions is in the denominator. So you look for restrictions in the denominator. In the denominator, we have 2x minus 1. We know that the denominator cannot equal 0. So basically, we're just solving this non-equation. We're solving for x to see what x can't be. Well, if we add 1 to both sides and divide both sides by 2, we find out that x can't be 1/2. What does that restriction represent? In this case, that restriction represents a vertical asymptote. Any factor that's in the denominator that you can solve for and find set equal to 0 or not equal to 0 and solve for x, that's going to lead you to a vertical asymptote because the function will not exist at that value. So we won't have any values along the x equals negative or x equals 1/2 line, that vertical line. There will be no y value. So that entire vertical line would be asymptote, somewhere that we're not going to cross. So we have a vertical asymptote at x equals 1/2. So I'm going to start using the bottom corner of this to start graphing or to start sketching. So I'm going to scroll down here. And bottom right-hand corner, I'm just going to sketch an axis, a vertical and a horizontal. And we know we have a vertical asymptote, not a horizontal asymptote, at 1/2. So I'm going to estimate that that's right here. And I'm going to say we have a vertical asymptote at x equals 1/2. Perfect, that's part 1. Part 2 is to state the domain. This doesn't help us graph it, but it helps us kind of have an idea. The domain will be all real numbers with the exception of any asymptotes or holes. And we'll look more into holes when we actually are graphing things that have holes. But for our reciprocal functions, there won't be holes. So, domain is x belongs to real such that, and our restriction is that x can't equal a half, such that x does not equal 1/2. And that's our domain. C asks us for behavior of the function near the vertical asymptote. So, to find that, we are going to do a test. We're going to test some x values that approach a half from the left side or from the negative side. Negative side of the number line is the left side of the number line, so we're going to pick an x value that's to the left of a half. And we're going to test it to see what the y value is. And to test it, we're going to plug it into the function. So we have to think, what is a value to the left of a half? We can start by trying 0, and 0 is kind of valuable because that would give us our y-intercept. If we plug 0 into our equation, 1 divided by 2 times 0 is 0 minus 1, so it's 1 divided by minus 1, which is -1. So for 0, we get -1. And we can actually plot that on our graph. We know that we have a point right here, and it's 0, -1. That's our y-intercept. Now we want to get closer to a half. So what's a value that's closer to a half? Well, 0.4. If we plug in 0.4, we get -5. So what this is telling us is that if this is -1, as we get closer, we're actually going down. So what we're going to assume here is that we're going to approach this asymptote and keep going down. Because once we start in one direction as we approach an asymptote, rarely do we change direction and go the other way. Just to be sure, let's do one more value. Let's do 0.49. If I plug 0.49 into our original function, we get -50. So that continues the trend of going down. So we can conclude as x approaches a half from the left, f of x is approaching -infinity. And we'll keep going down. To prove it, 0.499. If you're not entirely convinced, let's throw another 9 on there. That would be -5,000. So you might be convinced now that we're continuing to go closer and closer to -infinity. So what that tells us is that right here we're bending and going down. So we can put that behavior on the graph now. Okay. Part D. D says determine the horizontal asymptote. I said the horizontal asymptote is going to be 0 in the last video. Here's why. We can test, I skipped a part. We only approached from one side of the asymptote. Let's see what happens as we approach from the other side. As x approaches a half from the positive side. We do a similar analysis. We pick some x values and see what the function's doing. This time we're going to pick x values bigger than a half. So like 0.6. If we plug in 0.6 to our equation and solve, we get 5. If we plug in 0.51, we get 50. If we plug in 0.501, still bigger than half, we get 500. So you might see a trend here, 5, 50, 100, we're continuing to get bigger. That means that f of x is approaching infinity. That means we're going up on the right side. So we can put that behavior there too. We don't know what the rest of the function's doing yet, but we do know the behavior around the asymptotes, the vertical asymptotes. Now, back to the horizontal asymptote. To find out where the horizontal asymptote is, the function will usually level off around a horizontal asymptote as x gets really, really big or really, really negative. So as x gets really big, like goes towards infinity, wherever that asymptote is, the graph will approach it. So if the asymptote truly is at 0 as we approach infinity, we should get values closer and closer to 0. So as we plug in bigger and bigger numbers, we should get numbers closer and closer and closer to 0. And the question is, do we get them from above 0, so positive, or do we get them from below 0, or negative? Well, that's where the test comes in handy. So we can test for a horizontal asymptote by looking as x approaches infinity, what's happening to f of x? What does f of x approach? Well, we have to think, what are some numbers that are getting bigger? Or what are some big numbers that we can plug into our function? Let's start with 1,000. If we plug 1,000 into our function, you get 0.0005, which is a really, really small number, bigger than 0. What if we plug in 1,000,000? 1, 2, 3, 4, 5, 6. If we plug in 1,000,000, we get 0.1, 2, 3, 4, 5, 6 zeros and a 5, which is still above 0, but we're definitely approaching 0. So we are approaching 0 as x approaches infinity. As x gets really big, we're approaching 0 from the positive side, from above. So we can put that behavior on our graph. We know as we get big, we're going to level off to 0, and that's where our horizontal asymptote is. What about from the other side? What about as x approaches negative infinity? What's happening to f of x? You might be able to guess. It is going to approach 0. Is it going to approach from below or above? Well, right here it's below. Odds are it's going to approach from below. But let's test. Think of some numbers that are close to negative infinity. Well, not really close, but approaching negative infinity. We could say negative 1,000 and negative 1,000,000. Negative 1,000, if you plug it in, is negative 0.0005. And negative 1,000,000, if you plug it in, is negative 1, 2, 3, 1, 2, 3, 5. Both negative, both slightly smaller than 0. So we're approaching 0, but from below. So we have this behavior. We're below the x-axis. And you might say, hey, can't we just connect these two branches now? And basically, yes. Yes, you can. If you want a few more exact points, well, you could plug in like 1 and 2 and 3 and get some values out here. But they are going to be very close to 0, so we can just connect those now. The key points that you want on the graph are you want the behaviors around asymptotes, and you want any x and y intercepts. There's only a y-intercept in this graph because we don't cross the x-axis because that's where our horizontal asymptote is. Part E asks for the range. Now that we have a sketch, we can come up with our range pretty easily. We can see that it's basically every y value with the exception of 0, or horizontal asymptote. So our range is that f of x belongs to real such that f of x does not equal 0. Find the x and y intercepts. We've already found the y-intercept, but let's look for an x-intercept. We know there's not one because we didn't graph one, but how do you find an x-intercept? Well, x-intercepts occur when y is 0. So if we take our equation, f of x equals 1 over 2x minus 1, and set it equal to 0, we'd have 0 equals 1 over 2x minus 1. If we try to solve that, we can multiply both sides by the denominator, 2x minus 1, which would leave us with 0 equals 1, which is not true. Therefore, there's no x-intercept. To verify a y-intercept, kind of run out of room here, so I'm going to work up here. A y-intercept is when x is 0, so f at 0 equals 1 over 2 times 0 minus 1, and we've done this in the table already. We know it's going to be negative 1. If we solve it out, we get 1 divided by negative 1. So f at 0 is negative 1. Therefore, 0, negative 1 is the y-intercept. So to find the x-intercept, make y 0 and solve for x. No x-intercept. To find the y-intercept, make x 0, solve for y. Negative 1, we have a y-intercept. Part H asks us to sketch. We've already done that. We did it piece by piece. This is a full properties analysis of a rational function to come up with a graph. The new part, or the key part, that you're going to have the most difficulty with is the behaviors around the vertical asymptote and the horizontal asymptote. Looking for the restrictions or vertical asymptote, probably okay. Domain and range, probably okay. X and y-intercepts, x-intercept, we might need to practice that one a little bit. Y-intercept should be okay. This is the process we're going to use when we do our warm-up tomorrow. So this is what we're going to practice. Thanks for watching part 2. Pick that up in part 3.